Imagine kicking off a massive reinforcement learning job on an 8 billion parameter model. You fire up your cluster, right? But instead of standard practice, you freeze 97% of the network.
Which is terrifying for most engineers.
Oh, absolutely. You target just one single transformer layer right in the middle of the stack. You update only those specific weights. And when the evaluation finishes, your model isn't just competent, it's actually significantly smarter than if you had trained the entire network.
It sounds like a bug in the evaluation script, honestly.
Right. But for all the ML engineers and AI researchers tuning into AI paper slop today, we are dissecting a brand new, completely mind-bending preprint that proves exactly that.
Yeah, it's called Is One Layer Enough? Training a single transformer layer can match full parameter RL training.
And it's by researchers from the University of Minnesota, Peking University, and Amazon. Let me just give you the core insight straight away to anchor this whole discussion.
Go for it.
When we do reinforcement learning from verifiable rewards. So think RLVR or GRPO post-training to boost reasoning. We have universally assumed that every parameter in the network should get an update. But this paper definitively proves that updating all parameters uniformly is, well, it's highly suboptimal.
Extremely suboptimal.
Yeah. Training a single middle layer recovers almost all the performance gains, and crazily enough, it frequently surpasses the full parameter baseline. And these super layers are always found right in the middle of the transformer stack.
Which is just a huge paradigm shift for how we think about post-training adaptation.
Okay, let's unpack this. Because we are going to explore how they quantified this with a new metric called layer contribution, prove why this isn't just a fluke of weight change magnitude, reveal the shocking diversity of what these individual layers actually learn, and most importantly, give you practical, out-of-the-box strategies to immediately improve your RL training pipelines.
I mean, to really understand how a single layer can replace an entire network update, we first have to look at exactly how they isolated and measured these layers in the first place.
Right, because you can't just slice a transformer in half and see what happens.
Exactly. So it started with frozen, pre-trained base models, mostly the Qwen 3 family, and applied GRPO, Group Relative Policy Optimization, but they completely altered the backward pass.
How so?
They isolated a single layer, we'll call it layer K, and they restricted the optimizer to only update the weights inside that specific block.
So wait, the embedding layers are frozen, the language model head is frozen?
Everything.
And every other transformer block is frozen. But the RL signal still backpropagates down through the entire computational graph, right? Because it has to reach the middle layers.
Right, the gradient flows through everything, but the actual parameter update step, the part that actually changes the model, is isolated purely to layer K.
Okay, got it.
And they did this independently for every single layer in the architecture. So take the Qwen 3 1.7b model, which has 28 layers. They executed 28 entirely separate RL training runs from scratch.
Oh, wow. Just to observe the isolated learning capacity of each depth in the network.
Yeah. And to quantify this, they introduced this specific metric called layer contribution, or C of K. It's basically the fraction of full RL improvement that training layer K alone recovers.
So a score of 1.0 means it completely matched full parameter RL.
Precisely. It completely perfectly matched training the entire multi-billion parameter network.
Which sets the stage for the numbers because they are absurd.
They really are.
On mathematical reasoning benchmarks, using that 1.7 billion parameter model, layer 10 achieved a layer contribution score of 1.14.
A 14% boost over the baseline. By training just layer 10 and leaving the other 27 layers completely frozen, it didn't just match it, it comfortably beat the full network update.
That is insane.
And conversely, if you look at layer 24 on that exact same model, the score drops to 0.28.
So it barely recovered a quarter of the performance.
Yeah, we're seeing this massive structural discrepancy in where a language model actually absorbs RL gradients.
You know, reading that, it made me think of a 36-person corporate department taking credit for this massive multi-million-dollar project.
I love this analogy.
Right. And then an audit happens, and they reveal that one single mid-level manager layer 10 actually did 114% of the work. And letting the other 35 people, quote unquote, help, actually slowed the whole project down.
That's exactly what's happening mathematically.
But I have to push back a little here. Is this just a fluke on one small specific model? I mean, RL runs are notoriously flaky.
It's a fair question, but no. What's fascinating here is that the location of these quote unquote super layers is remarkably consistent. It reveals this hidden structural property of LLMs.
A sort of Goldilocks zone.
Yes. Across all the models they tested, high contribution layers consistently concentrate in the middle of the transformer stack, roughly around 40% to 60% of the network's depth. The early and late layers just contribute substantially less.
Even when you scale up the parameters.
Even then, this holds true across scales. They tested Qwen3 at 1.7B, 4B, and 8B. And even on the 8 billion parameter model, layer 16 scores a 1.07.
So it's still beating full parameter training.
Easily. And it wasn't just standard GRPO. They tested algorithmic variants like Dr. GRPO and GGPO. They tested Qwen 2.5 architectures. They even tested the DeepSeek distilled Qwen 7B model.
Wait, distilled models have this structure too?
Yes. Which proves that even when you compress knowledge from a massive teacher model, the architecture still organizes that knowledge by depth in the exact same way. The middle layers are still the heavy lifters.
And what about the actual tasks? Math is superstructured. Does this hold up if the model is, say, writing Python?
It does. It works for mathematical reasoning on datasets like math and Newman math, but also coding capabilities using DeepCoder and even multi-step agentic tasks using ALF World.
Really? Across all of those?
Yeah, the cross-task consistency is wild. If you rank layer importance on a math dataset, that exact ranking transfers highly to another math dataset with a Spearman correlation of 0.76. And it even transfers to a coding dataset with a correlation near 0.60.
So a layer that is highly adaptable for math reasoning is also highly adaptable for code generation.
Exactly.
Okay, well, here's where it gets really interesting for the ML audience. If the middle layers always win, is it just because the backpropagation gradients naturally cause the middle weights to change the most during normal training? Like, is this just a mechanical step size issue?
It's the most logical assumption, right? That the middle weights just physically move more. So the researchers directly investigated that by looking at the absolute L2 norm of the weight changes.
Basically measuring how much the parameters actually shifted.
Right. But the data completely shatters that gradient hypothesis.
Oh, really?
Yeah. During standard full parameter training, the weight change magnitude is remarkably uniform across all layers. It ranges between like 0.5 and 0.8 for basically every layer. The middle layers do not move more than the others.
So the optimizer is applying equal physical effort across the whole network.
Yes. Now, during single layer training, where only one layer is allowed to move, that single active layer does compensate by taking a slightly larger step in parameter space. The L2 norm jumps to about 0.8 to 1.0.
Okay, that makes sense. It's doing all the work.
But crucially, whether it's a high contribution layer like layer 10 or a low contribution layer like layer 24, they both shift their weights by the exact same magnitude when trained in isolation.
Wait, layer 24 is changing its weights just as much as layer 10?
Yes.
But it's recovering barely a quarter of the performance.
If we connect this to the bigger picture, it proves that lower contribution is about what is learned, not how much the weights shift. It reflects the intrinsic effectiveness of a layer's parameter subspace to absorb RL signals.
It's like two people walking the exact same distance. The magnitude is identical. But one person walks a mile in a straight line and successfully crosses the finish line, representing high contribution.
Right.
While the other walks a mile in circles and goes absolutely nowhere. The step size is irrelevant if your starting location, your subspace, doesn't offer a clear path.
That captures the mechanics perfectly. The early and late layers just don't have a parameter subspace oriented toward complex logical adaptation.
Which creates a fascinating puzzle. If these middle layers are successfully finding the finish line in parameter space, does that mean they are all learning the exact same optimal policy?
Like, are they redundant?
Yeah. If I train layer 10 and you train layer 13 and they both get a massive boost, I assume they just independently converged on the same set of mathematical heuristics. Let's look at what the models actually output.
So the researchers had that exact same suspicion. They explored the Jacquard similarity between the problems solved by the top 7 single-layer models on Qwen 3.1.7b.
Basically checking the exact overlap of which test questions they get right.
Exactly. And the overlap is shockingly low. It's only 34.1%.
Wow.
For instance, layer 10 and 13 only shared about 31.9% of their newly solved problems.
Yeah.
They are solving completely different subsets of the dataset.
They aren't redundant at all.
Not even close. And to prove the utility of this, they did majority voting using an ensemble of those top 7 layer trained models. This ensemble hit 33.6% accuracy on Olympiad bench.
We need to contextualize that. The best single layer was 28.3%. The standard full parameter RL model was only 26.9%.
And if you take 7 different samples from a full parameter model and standard self-consistency, it only hit 31.3%.
So training single layers creates wonderfully diverse, specialized experts along the depth of the transformer. That is an incredible analysis tool. But, okay, putting my ML engineer hat on, how does an engineer actually use this today without training 36 separate single-layer models?
Because nobody has the budget for that.
Exactly. The compute overhead would be a nightmare.
Well, the paper translates these theoretical findings into 3 immediate, practical, layer-guided training strategies that you can use right now.
Let's map them out.
Strategy 1 is layer adaptive learning rate. You just boost the learning rate to, say, $1 times $10 for the top K layers, while keeping the rest at the default, which is usually around $5 10 to 6 times.
And what's the result?
Consistent improvement. You're just telling the optimizer to trust the gradients more heavily in the subspaces capable of meaningful adaptation.
Makes sense. But what if we go further? Like, if the early and late layers are just acting as noise, why even let them learn?
Which brings us to strategy 2, layer selective training. This one is way more aggressive. You freeze the quote-unquote bad layers completely, no updates at all, and you only train the top 5 or 10 layers.
I'm guessing the gains are bigger.
Massive gains. On Qwen 3.8b, training just the top 10 layers hit 69.1% on math. It completely destroyed the full RL baseline, which was 66.4%.
Almost a 3-point bump just by stopping the bad layers from participating. Plus, you save so much VRAM by not keeping optimizer states for those frozen layers.
Exactly. But there is a catch. To do strategy 1 or 2, you have to find the top K layers first, which requires expensive profiling.
Right, you still have to run the single-layer sweeps to find the top performers.
Unless you use strategy 3, heuristic layer selection, because of the quote-unquote middle layer phenomenon we talked about, you can just blindly select the middle K layers based on their index position.
Oh, wow. So on a 36-layer model, you just pick layers 15 to 19 and freeze the rest.
Exactly. 0 profiling required. And the heuristic strategy consistently beats the full parameter baseline across all 3 Qwen 3 scales.
Yeah.
It captures up to 21% of the total RL gain above the baseline, entirely for free.
So what does this all mean? The ultimate takeaway for you running RL jobs this week is that standard uniform RL is highly suboptimal.
It really is.
Updating bad layers actually dilutes the model's performance, like adding noise to a perfectly clean signal. The middle layers are the undisputed heavy lifters in RLVR and GRPO post-training. By simply freezing early and late layers, you save compute and achieve higher performance.
And this raises an important question, something really provocative for the community. The paper proves that RL naturally creates highly specialized, diverse experts in different middle layers. They literally solve completely different subsets of problems.
Yeah, that 34% overlap stat is crazy.
Right. So if a model's intrinsic structure naturally rates different reasoning tasks to different layers, could we design future RL reward models to explicitly encourage this?
Oh, I see where you're going.
Imagine a training paradigm where we don't just freeze layers, but actively force different depths of the network to master mutually exclusive subsets of the data.
Essentially building a mixture of experts out of a standard dense transformer's depth.
Exactly. A Depth-Wise MoE driven by targeted RL, completely eliminating the routing overhead of traditional MoEs.
That is an incredibly wild thought experiment. Thank you to all the ML engineers and researchers for tuning into this analysis on AI Paperslop. Keep challenging those default training configurations and seriously consider hard freezing a few layers on your next post-training run. We'll catch you on the next deep dive into the research.